Hey there, we're going to look at 4.9 today on roots and zeros. This is the last section of chapter 4, and so the plan will be that tomorrow, Friday, we'll have a quiz on 4.6 and 4.9, and then after the wave week, we'll look at the test for chapter 4. But let's look at what we're dealing with today. Objective. Students will be able to do the following. They'll be able to determine the number and types of roots of a polynomial equation, and then be able to find the zeros of a polynomial function. And this falls under the standard PR3, graphing polynomials while identifying zeros with pseudo factorizations and indicating end behaviors. Okay, and so let's kind of just review for a second, a little chart here. And you might want to pause, just review some of this information, but this is what we've talked about all chapter and really going all the way back to chapter 2. What are zeros, what are factors, what are roots, what are intercepts, right? So remember that the zeros of a function are -3, 2, 1, and 2 for this example function here, right? And remember, the zero is of a function. A root or solution is when p of x is equal to 0, right? So we're solving the equation equal to 0. And so those would be -3, -2, 1, and 2, right? The factors would be when we factor this out. X plus 3, x plus 2, x minus 1, and x minus 2. Remember, the x lies to you because remember you're doing x plus 3 equals 0, and that's what gives us the -3 there and there, right? And so then our x-intercepts of the graph is where on our graph this is crossing or touching the x-axis, and so those are those 4 ordered pairs in this case. So that's what we're looking at when we talk about those 4 different things. And again, we're talking about these terms interchanging with one another. So the first thing we're going to talk about that's new today is this fundamental theorem of algebra, and it states that every polynomial equation with degree greater than 0 has at least one root in the set of complex numbers. So it might mean it's real, it might mean it's imaginary, or it might mean it's a complex number. So let's see what that means to some example problems here. And so looking at example 1, we've got a simple quadratic here, x squared plus 2x minus 48 is equal to 0. We want to state the number and type of roots. Well, if I solve this out, right, if I try to factor this, right, so I've got the -48, and I'm trying to get to positive 2, what times what's going to give me -48 and add to positive 2. Well, that would be a -6 and a positive 8. So subfactor to x minus 6 and x plus 8 equal to 0, right? So x minus 6 equals 0, or x plus 8 equals 0. So x is equal to 6, or x is equal to -8. So this would have 2 real roots, right? Because these are real numbers. They're not imaginary or complex. Okay? So, and that's what we're looking at. It's being able to simplify these out so that we see what solutions they have. So let's look at another example. We've got y to the 4th minus 256 is equal to 0. So we're going to get that y to the 4th is equal to 256, which means that y is equal to what? Well, I'm going to take the 4th root of both sides. And like we do when we take a square root, a 4th root is going to need that plus or minus. And so what is the 4th root of 256? Well, that is just 4, because 4 times 4 is 16, and 16 times 16 is 256. Now, what does that mean, though? I've only got 2 numbers here. I've got positive 4 and I've got -4. But here's the thing, and we're going to talk about this in a second. When I look at this function and I actually graph it, right? If I graph y to the 4th minus 256 equals 0, what we see is this, is that at -4 and at positive 4, this graph's going to go through, and then when we get all the way down to -256, we're going to see it come through -256 and come back up, right? Now, here's the thing, it just goes straight through these 2. So these 2 are real roots, right? So it has 2 real roots. But what we're going to see in a second is that a 4th degree polynomial has to have 4 roots. And so if this has 2 real roots, it means it also has 2 imaginary or complex roots. And so that's what we're going to lead to with the theorem that we're going to see in a second. And we would see the same thing here on a to the 4th minus 81 is equal to 0, right? So if I have a to the 4th minus 81 is equal to 0, we're going to get that a to the 4th is equal to 81. And taking the 4th through both sides, we get a is equal to positive or -3. And so again, we're going to see our graph, -3 and +3, and all the way down here at 81 is going to cross through like so. Again, looking somewhat like a parabola, not completely because it's steeper because it's a fourth power, not a second power. So I've got two real roots here as well, but again, the power's 4, so that means I have to have two imaginary or complex roots. Okay, and so what that theorem that we're going to have is this. So remember the fundamental theorem of algebra said I have to have at least one root if the degree was greater than 0. Well, the corollary is this, is that if the degree is n, so degree is 2, degree is 3, degree is 7, right? It has to have exactly that many roots in the set of complex numbers, including repeated roots. Now, what does that mean? Well, when we look at like x cubed so we're going to talk in roots, right? So the function f of x equals x cubed, right? And that graph comes through like this. Well, when I set it equals 0, I just get that x is equal to 0. So that's the only root I have. But that's actually a repeated root there at the origin. So let's talk about Descartes' rule of signs. Now, this is a property that some people get confused, but it's not that hard once we look through a couple of examples. So all of this says is we have some polynomial of some degree, right? And it says it has to have real coefficients. So Descartes' rule of signs says that the number of positive real zeros of our polynomial will be the same number of changes in the sign, again, the changes in the sign of the coefficients of the terms, or less than that by an even number. And then the signs, or the number of negative real zeros, is the same as the number of changes in the signs of p of negative x. Now, what does that mean? That means I plug in negative x for all the x's that I see. And so, or it could be less than that by an even number of, as well. So, again, we could talk through this property, but the easiest thing is just to look at a problem and see what it actually means. Now, remember our standard is that we only deal with third degree polynomials or less. It's easier to see this in action with higher degrees because you need different terms involved here. And so what we're going to set up is we're going to ask ourselves how many positive roots am I going to have, how many negative roots am I going to have, and how many imaginary / complex roots, right? And remember what our corollary said, right? Our total will always be based on the degree. Well, the degree of this polynomial is 6, okay? And so the first part of Descartes' rule says if I take just the regular function, I look at all the changes of the signs, and that will be the number of possible positive real zeros that I have. And so let's look at our signs. We start negative. It changes to positive, so that's one change. Our positive changes back to negative. That's a second change. It stays negative, so that's not a change, and then it stays negative. So I could have two positive real zeros. But it also says that it could be less than that by an even number, so I could subtract 2 or 4 or 6. Now, obviously, I can't have negative positive real zeros, so I could take 2 minus 2 and get 0. So those are my two possible cases. I could have for positive real zeros, my options are that I could have 2 or 0. So let's talk about negative. So we do p of negative x, which means everywhere I see x, I replace it with negative x. And so it's going to make this problem look really weird for a second, but we'll work through it. Okay? So, dealing with our powers. If I have the negative of something to an even power, it comes out positive, right? So p of negative x equals negative x to the 6th, because this sign will go back to positive and the negative sitting out front. This is to the third power, so the negative is going to stay, so I get negative 4x cubed. This is squared, so this will become positive, and so that negative out front will stay. Negative times negative is a positive, and so minus the 1 at the end. And so again, we're going to look at all of our sign changes. And so it starts negative. Negative to negative means I'm still at 0. Negative to negative, negative to positive, that's my first sign change. And positive negative makes my second sign change. And so how many negative real zeros could I have? Well, again, how many sign changes were there? There was 2, or I could reduce that by even, so I can subtract 2 and get 0. So I could have 2 positive 2 negative, or I could have no positive and 2 negative, right? And so looking at combinations here, I could also, again, deal with that. And I could have no negatives associated with my positives, right? So I could have 2 and 2, 0 and 2, 2 and 0, or 0 and 0. Those are 4 cases that I have right now. Now, remember that our total has to be matching the degree. So all of these have to total to 6. And our imaginary or complex roots will always finish the tally. So 2 plus 2 is 4. I got to get to 6, so I can have 2 imaginary or complex roots. 0 and 2, so that's only 2, so getting to that would leave me 4 imaginary or complex roots. 2 and 0 would leave me 4 again to get to 6, and 0 and 0 means that all of my roots could be imaginary or complex. And so this is my table based on Descartes' rule of signs of the possible numbers of real zeros and imaginary zeros, both positive and negative in terms of real. Now, could we graph the function and narrow this down and know what it's going to be? Sure. But Descartes' rule of signs allows us to know the possibilities of what we have before we even do any major lifting to this problem. Okay? So let's look at a second example. So we've got x to the 6th minus x to the 3rd plus x squared plus x plus 3. And so we're going to do the same thing. Remember, with the p of x, we're going to do it first with our sign. So going from positive to negative, that's my first change. Negative to positive, that's my second change. Positive to positive, not a change. Positive to positive, not a change. And so the positive real zeros could be 2 or it could be 0, right? And so again, we could start to set up our table: positive, negative, imaginary complex, and then our total, right? Well, again, in this case, my total will be the degree, so that is 6. And right now, I could either have 2 positive or no positives, right? Now let's deal with the negatives. And so I'm going to do p of negative x. So everywhere I see x, I'm replacing it with a negative, like we did in the previous problem. Make sure your signs are all right. And so as we go through this problem, let's check out what happens when we simplify. So again, to an even power, that's going to become positive. Odd power is going to keep it negative, but a negative times a negative is a positive. Negative squared is going to give us positive, and the sign up front was positive. Positive times negative is negative, and we've got the plus 3 on the end. And so let's check out our signs here. Positive, positive is not a sign change. Positive, positive, still not a sign change. Positive to negative, that's our first sign change. And negative, positive is our second sign change. And so how many negative real zeros might I have? Well, again, it could be 2, or it could be 0, because I can reduce down by even numbers. And so my negatives could start out with 2 or 0. And I've got to have all the other combinations, and so I could again have 2 or 0 here, and I could do 0 and 2 here, right? So again, making sure I have all the combinations: 2 with 2, 0 with 0, 2 with 0, and 0 with 2. And again, we're adding up to 6 for all of these, and so 2 plus 2 is 4, so I leave me with 2 to get to 6. 0 and 0 would give me all 6 being imaginary or complex. This will leave 4 and 4. So again, Descartes' rule of signs shows me that these are the possible combinations. Now, again, only one of them would actually be true. We could graph it to determine what that's going to be, or we could factor it if it's factorable, things like that, to determine what our zeros are going to be. Okay? So again, Descartes' rule of sign is not complicated. Now, we could use synthetic division to find our zeros. And so one of the things that we didn't talk about, and this is one of the lessons that we skipped, but understanding that when the remainder of synthetic division comes out to 0, what it means is we found one of the factors, right? And if it's one of the factors, that means we could solve that to find one of the zeros or roots of the function, okay? And so find all the zeros of this. So I'm going to use synthetic division: 1, -1, 2, and 4. Now, again, if we were dealing with this in pre-calculus, we would talk about a method of finding the possible real zeros. What we're going to do here is just go to the graph and determine where our zeros might happen and see if they're real or not. And so as we look at the graph of this, we see that it only has one place where it crosses the x-axis, and that's at -1. So I'm going to put the -1 here. And so watch what happens. Remember, the first number is going to just drop straight through, and then we multiply these, so -1 times 1 is -1. We're always going to add in the middle, so -1 plus -1 is -2. Multiplying, -1 times -2 is a positive 2. 2 plus 2 is 4. -1 times 4 is -4, and 4 plus -4 is 0. And so remember that our powers go down, right? So this is x to the third, x squared, x, and our constant. So this is our x squared, x, constant, and remainder. And so this comes out to x squared minus 2x plus 4. And so now we need to deal with a method to get our zeros that are not real, because this is the only place we have a real zero, right? And if we did Descartes' rule of signs, we would see that there's one sign change, two sign changes, right? And so the possibilities there could have been two positive real zeros, but if we look at the graph, there's none, right? Because 2 minus 2 is 0, so we could have none. But if we deal with negative f of negative x, we would see that this would be negative, this would still be negative, this would be positive, this would be negative, and this would be positive. So in the end, we would get one sign change here, so we had to have one on the negative side. Now, how do I find the other zeros? Well, remember, we could set this equal to 0, right? And so this is not going to factor, but I could do completing the square, or I could do the quadratic formula. I'm going to complete the square here because that's going to be the easier method of the two. I'm going to subtract the 4 to the other side. And then we're going to add in, remember, we're going to add half of the b squared. So half of the b would be -1, and squaring that would give me +1. So I'm going to add 1 to both sides. So x minus 1 squared is equal to -3. And I'm going to run out of room here a little bit, but so x minus 1 is equal to positive or negative square root of -3. Adding the 1, we're going to get that x is equal to 1 plus or minus, I've got this negative inside, so the I is going to come out, square root of 3. So my 3 zeros, because it was a third degree function, right? So my 3 zeros will be the -1 that we had here, because we verified this, and that's through remainder theorem. And we'll talk about that in pre-calculus. But my 3 zeros are going to be -1, and then 1 plus or minus I root 3. Okay? And so that's it. Again, if we can get all real zeros, we'll get all real zeros. If some of them come out imaginary or irrational, we'll deal with those as they come. So let's look at example B here. We're going to do the same thing. We're going to do synthetic division. So we got 1, -3, -2, and 4. And we're going to use our graphing calculator to see where these zeros might happen. Again, pre-calculus, we'll learn about our P's and Q's to deal with it in a little bit different method. But we'll go to our graph. And so as we look at this graph, we're going to see that there's 1 0 here, another one here, and another one here. But these two, this first one here that's in the negatives and this one here in the positives, doesn't cross at a really nice value. But this one right here does. And so I'm going to try 1 first. Again, if I don't get 0 for the remainder, then it doesn't work, right? We've got to get 0 here through the remainder theorem. So the 1 drops through. 1 times 1 is 1. -3 plus 1 is -2. 1 and -2 gives me -2. So this will give me a -4, because remember we're adding vertically here. 1 times -4 is -4, and 4 plus -4 is 0. And so we end up, again, remember we deal with our powers dropping by 1, and so this is my x squared, this is my x, this is my constant and remainder. So I get x squared minus 2x minus 4 for the polynomial that is left. Again, we will complete the square here to be able to solve this, so we set this equal to 0. And so I'm going to get x squared minus 2x plus my blank is equal to 4 plus my blank. And so what's going to go in the blank? Remember, it's half of the b squared, right? Half of the b squared, so half of -2 is -1. Squared is +1, so I add 1 to both sides. So this will be x minus 1 squared is equal to 5. And so coming to here, we're going to get x minus 1 is equal to positive or -5. Adding the 1, we get x is equal to 1 don't forget the square root here, plus or minus the square root of 5. And if we look at those two values, square root of 5 is about 2.2. And so if we take 1 plus 2.2, we get about 3.2, and that's about where that is. And if we take 1 minus 2.2, that gets us about negative 1.2, and that's where that point is. And so our list of zeros will be 1, and then 1 plus or minus the square root of 5. And so that leads us to two theorems here. The first is the irrational roots theorem, which says this: if a and b are real numbers and b is not equal to 0, then a plus the square root of b is a 0 of the polynomial with real coefficients, and a minus the square root of b is also is also 0 of the function. And so the reason is because when we take the square root, remember, we get both the positive and the negative of it. And so that's represented here and here. Okay? And so complex conjugacy theorem does the same thing, except because remember, we're still dealing with square roots when we deal with complex numbers. It's just that that complex number had a negative inside, and so it comes out as a what? As an I, right? And so, again, that real coefficient could be under a radical. It could be the square root of 7, right? So again, understand that this is not going to be any different than what we had before, okay? And so the last two examples here we're going to look at is going to do this in reverse order. Is we're going to be given the zeros of the function and we want to write the polynomial of least degree. And so if I'm given that one of the zeros is 4 and the other one is 5 minus the square root of 3, well, go back to the theorem we just talked about. If I have one zero that is a minus the square root of b, then I also have to have a plus the square root of b. And so it means another one of my zeros is 5 plus square root of 3. Now, if these are my zeros, then I can plug them in as factors. So x minus the 4, x minus 5 minus square root of 3, and then I'm going to have x minus 5 plus the square root of 3. Now, I'm going to show you a little trick here on multiplying these out, because this and this will come out to a difference of squares which will multiply. So I'm going to leave this x minus 4 in the front for a second, and we'll come back to it. And so distributing this negative here, I'm going to get x minus 5 plus the square root of 3, and then x minus 5 minus the square root of 3. Now, again, the associative property says I can group things, right? So if I group this, like so, this is my a, and my square root part's the b. And so what I'm going to get, remember, is going to be a squared minus the b squared. So I'm going to get the x minus 5 squared minus the square root of 3 squared. And again, that comes from the property a plus b times a minus b is equal to a squared minus b squared. And again, the a and the b can be anything that we multiply together. And so simplifying this, what we're going to get, just multiplying this out, we're going to get x squared minus 10x plus 25 is going to be minus 3. Now, how did I get that? Remember that if I have a minus b squared is equal to a squared minus 2ab plus b squared. Okay? Again, things that we're just bringing back up from previous sections and previous chapters. And so simplifying this part, we're going to get x squared minus the 10x plus 22. Now, remember that little x minus 4 that's been hanging out front all the way, and we're going to just drop it on down all these lines? I'm finally going to multiply it to what I have in the blue. And so our easiest method would be to break out our box. And so I'm going to get x squared minus 10x plus the 22 and x minus the 4. So I'm going to get x cubed. This is going to be negative 10x squared, 22x, negative 88, positive 40x, and negative 4x squared. And so combining my like terms, I get x cubed minus 14x squared plus 62x and minus the 88. And so they all have integer coefficients, so I'm done. I don't need to do anything else here to simplify this or anything else. This is the final function. Again, we could put the f of x in front of it because we're talking about the zeros of this, so f of x is equal to this. But that's it. Again, it's not complicated if you think about what you're doing. You take everything that we've done since chapter 2, combine it all together in this section to kind of get it all in one fell swoop. I've got one more problem here, and it's got imaginaries involved, but I will tell you that it's the same steps as this, except instead of having 5 minus the square root of 3, you'd have the 1 plus I, and then of course with the complex conjugate theorem, you'd also have the root 1 minus I. And so if you'd like to try the example, great. If not, I'm just going to leave it there with those thoughts because this video has now gotten to 25.5 minutes. So on that note, I will tell you that the word of the day is complex conjugates. Again, the word of the day is complex conjugates. Make sure you get that word of the day in the Google form for your attendance for today. And again, please make sure you turn in your assignments, and I will catch y'all next time.